Happy late morning. I'm Chris Lentz. I'm here with my colleague Gabriel Cuomo. We're here today to talk about real-time stream processing architecture that we built at Comcast. But we've been big fans of the conference, so thank you for being interested. It's a pretty quick talk today. We really want to tell you who we are and what we do, so it helps explain some of the decisions we made in architecture. And then we're just going to jump right into the architecture, and it's some of it's pretty high level, and then we'll get into some of the details that. But basically, if we go too deep or we don't go high enough, we're hopefully going to have some time for some Q&A. We have sort of a SNAKE acronym. We get made fun of a lot for this, but it stands for Video IP Engineering and Research. And our team's basically spread out of Denver and Philadelphia. But we're responsible for basically everything under the video IP umbrella, delivering video to the customers on mobile, set-top, just various devices. So we're not the cable side of it. We're the IP video side of it. But basically, if you're going to watch Breaking Bad and you hit play, the life cycle video delivery starts way up in the preparation phase, where we basically transcode MPEG-2 into multi-bit rate MPEG-4, and then it gets sliced into what we call video fragments. Those get pushed out to a content delivery network. So when you hit play, you're getting fragments off of a CDN. It's something we call adaptive bitrate streaming. So there's lots of opportunity in this architecture for data analysis, which is what we're here to talk about. Specifically, we pulled out this slice of the pie. Big open source fans. And we work with a number of different vendors, but we're really here today to talk about the real-time slice of the world. So why do we focus on real time? Pretty obvious first bullet point, we want to be proactive. We don't want to be reactive. Common pattern in computer science, software engineering is you go look at logs when there's an issue. But when you put customers first, we want to basically react, proactively act in real time, basically. And we want to form real-time intelligence. And what we mean by that is we want to go beyond basic real-time analytics. So, things like aggregations and streaming averages are wonderful, but we have many use cases to bring mathematical models, things pulled from machine learning into real time. So that's pretty key for us. And all this is in the name of delivering the best quality video experience to users. So diving in, and again, there's a lot to talk about. We thought it'd be a much more easier conversation to really drill into the video player side of the world. We basically built a protocol that lives on the various devices you see up there in that familiar cloud we have scattered on all these diagrams. It would basically support live and on-demand. So we had to build an extensible protocol that can live, whether it's Xbox, Android, iOS, but that is what gives us rich events that can really tell us the video experience perceived by a customer. We basically carry those events in complex JSON objects. Just to highlight some of the key metrics, bit rate, just to go back to what I was saying about adaptive bit rate streaming, it's basically the quality of video being delivered to your player. The frame rates, the smoothness of video, and then the fragments that I mentioned are pulled off a CDN, various metrics around that. You don't want to be dropping fragments. And errors, of course, we don't like seeing, but all of these combined together make up the video experience, not necessarily one individually. So the cloud over there is basically depicting all these players pumping events down into our cluster here. So to go further, what we really need to do is basically form sessions in real time. We have a stateless protocol, so it's important that we basically stitch these events together and form what we call a player session. It's not much different in terms of if you think of what a web session is. We're doing the same thing with video analytics. So just to take a step back a bit, the high-level architecture, we use Flume as a distributed log collection tier. And this may be familiar to a lot of you, where we basically split two paths. The side on the right, we do lots of really cool work in the Hadoop ecosystem. We typically batch large LZO files down that land in our cluster about every 30 minutes. And the reason for that's probably pretty obvious. We try to fill block sizes and really get efficient use out of MapReduce there. But we're really here, again, to talk about the red side of the world over there, the red clouds, where we're pretty excited because we're doing real time within a second. And what that means is by the time an event lands in Flume and it's available for, streaming average and aggregation, but it's also able to be queried at that same level. It's not just the computation of a metric. It's literally available for an analyst to query. So this is where we're going to dive a little bit deeper, and Gabe will come up and talk about the Flume side of the world here.
Thank you. So now that I'm Gabriel Como, now that Chris has laid down the context and the overview of architecture, let's indeed dive a little deeper into the real-time paths. And we'll first approach it in a generic way, and then more specifically with our use case at Comcast. So let's start with Flume. So I guess most of you are already familiar with Flume, so I'm going to zip through that slide. It is a system to collect, aggregate, and move large amounts of data. It is distributed, done the right way, therefore it's scalable and reliable. One of the reasons why we also like it very much is because it's very customizable. Most of its components can be tailored to specifically fit our needs. Flume is composed of agents which are independent from one another. They're usually architected in the multi-tiered formation, like depicted on this already simplified diagram. Each agent is itself composed of sources which ingest the data, channels that are temporary queues, and sinks that forward the data to the next hub, whether it be a data storage, like HDFS, for example, or another Flume agent. The next important subsystem in our architecture is Storm. So Storm is a pretty popular distributed real-time computation system. It can be used in various use cases, such as distributed RPC, stream processing, or continuous computation, which we're specifically interested in today. Numbers is the equivalent of the job tracker in the Hadoop ecosystem. To Nimbus, you submit topology, which is a piece of code that defines spouts, bolts, and the way to link them. A spout is the source of the data stream. It emits messages, also called tuples, down the topology down to bolts. A bolt is a single computation unit which processes the data and eventually emits other tuples downstream. So, as Chris mentioned, we're interested in forming advanced analytics in real time, and especially summarizing data. So you may wonder, well, why do you do it in Storm? Why not just do it in Flume? That's a good question. So there's you could, but there's a few reasons why we don't. And as much as I'd love to give you the long version of our story, time constrains me to stick with just a few bullet points. So, first of all, there are technical issues that you need to tackle. And Storm has this concept of field grouping, which is implemented using a consistent hash. That ensures that all the messages that are related are processed by the same bolt. Also, Storms comes with an exactly one semantic, which ensures that the messages are processed once and only once. Those two features are currently lacking from Flume. But there's a more fundamental reason why we decided to bring Storm into our architecture, and this is that Flume and Storm has been designed with different goals in mind. See, Flume it excels at collecting data, moving it around from various sources, decorating, filtering. Storm is built to be a computation system. So ultimately, separating concerns into two distinct systems naturally fits the semantic of our architecture. So you may also wonder, well, with session, what about write-through rates? So although we do save on storage space by summarizing the data into sessions, and we also reduce the computation duration of MapReduce jobs, the write-through rates remains the same, and that's because every analytics event that flows into the system is very likely to modify the session somehow. So the frequency of the update to the session objects remains the same. So now let's see a concrete example of how you would form a video session out of a stream of stateless analytics events if you were to work for Comcast IP Video Engineering Group. So in reality, things are always more complicated, but basically our Flume architecture boils down to two main tiers. The first one we call edge tier because it's on the edge of our data center. The analytics events that Chris talked about earlier are sent from the video player using HTTPS. So naturally, the edge tier agent starts with an HTTP source. There's an interesting use case, an optimization that we did in Flume that I'd like to mention as it may be of interest to you. And this is the way we rebatch the data that Flume receives. See, because the video player sends the analytics data as close to real-time as possible, this implies that Flume receives a very large amount of very small batches. And this isn't efficient for Flume because each batch corresponds to a transaction. And when you have a file channel, for example, this translates into a small I/O operation, which is obviously not efficient. So in order to fix that, we use a combination of memory channel, inner sink, and source, which are Avro sink and source, by the way, in order to merge all those small batches together in memory. The second tier of agent we call mid-tier because they're kind of in the middle of our architecture. And this is a very CDN-like terminology. And there's 2 points to consider here. The first one relates to video player event processing. And we do that in our custom player message interceptor. And that's the way we chain what we call event processors. So an event processor is a very small piece of code that performs a single operation on the analytics message, either decorating or filtering the message. So in our case, decorating might be adding geolocation information to the analytics events or adding video asset metadata information, stuff like the movie title, the list of actors, the duration of the movie. Filtering may be based on validating that the analytics events follows our specification or selecting which messages should go to Storm. But in order to manipulate the analytics events like that, we first need to convert them from Flume events into Java object that better represents our data model. And so the player message interceptor first deserializes the analytics events, run them through the chain of event processors, and finally reserialize the modified event back into a Flume event, or not if it's been filtered out. The other important task of the mid-tier agents is to fork the analytics traffic into two distinct streams, and this corresponds to the two paths that Chris highlighted in the overview diagram. So on the one hand, we have the traffic going to HDFS through, as you would expect, an HDFS sink, very standard use case here. The other one, the other data stream, only contains the analytics events related to real time and is sent to Storm using the Storm sink. So what is the Storm sink, you might rightfully wonder? Well, I happen to have a slide to answer it. So the Storm sink is a component of the connector that we built in order to bridge Flume to Storm, and that we very inspiringly called Flume to Storm, right? So because it's actually a generic problem and that it's one of the most requested features in Flume's Jira, we decided to open source it. So we're still working on releasing it to the community, so stay tuned. It should be available in the coming weeks. So when we designed this connector, we set a few design goals for ourselves. The first one is that we based the connector on the service discovery pattern. So naturally, we rely on Zookeeper because it's one of its common use case. the service discovery also provides for a very simple minimum configuration that's very elegant. All you need to do is to specify a zookeeper quorum connection string and some identifier to identify the groups of sinks. We also wanted it to be distributed and scalable and reliable like any other parts of our system. And because we work in the real-time space, we also wanted to achieve as low latency as we can. And that's why we use Cryo as serialization layer, just like Storm uses, by the way. So in a nutshell, this is the way it works. So you have the Storm sinks in Flume that connects Zookeeper and register their presence. The Flume spouts in Storm connects that same Zookeeper quorum, locates the sink, and connects to them. The Storm sink in Flume just distributes the Flume event to its connected spouts. So in summary so far, this is what a simplified video player Storm topology can look like. So we have the analytics events generated by the video player that flows into Flume, and Flume, using the Flume to Storm connector, pass those events to Storm. The Flume spouts in Storm converts the analytics events into tuples and emits them down the topology, primarily to the session bolts, which are going to form session, like Chris mentioned earlier. But they can be also emitted to other tuples that may perform other tasks, such as computing fragment metrics, for example. So now that the session, the video session are created in Storm, and in other words, they're in memory of the Storm bolts, we need a way to provide that information to other systems. And I will bring back Chris in order to provide more insight into how to do next, what to do next.
So we're assuming that most people want to write data out of Storm, because we've gone through some interesting iterations. We'll sit in our lab. It's definitely technically possible to query Storm bolts directly out of memory, but you only have volatile per assurance. So the common case is going to be to push data out of Storm. So the question is, how do you do that, and what sort of requirements do you have to do so? I mean, first, we wanted to go past key value stores in terms of functionality. And what I mean by that is we have very good use cases to write to something like HBase, and we do. But you're limited, right? You doing secondary indexes is a difficult thing to do in HBase. It's very, very possible to do if you have coprocessors or you're using Solr as secondary indexing. But once we started really working in real time, we start to feel like we need to do something sort of SQL-based, right? Even a simple group by. But doing secondary indexes is pretty key to us. We also have the requirement to do real-time and historic, at least tiny movements of windows historically, and we don't want to go to different systems to do that. Once we start going back too far in time to look in a historic window, you start going, okay, I'll go back to Hadoop and do that type of work. But a sliding window of, even a week is very much a realistic requirement for us. Once we really start thinking through this, what we really want is the speed of in-memory writes and the durability of disk, and it goes back to the volatility of just writing to memory. So those are pretty key requirements there. So what works for us is basically using MemSQL as a persistent store. And for those that you don't know, it's basically a distributed in-memory SQL database. So we're able to do true distributed queries. Essentially what we're doing is sharding data down to the point where everything's in memory. But basically the way it works, and by the way, if you're familiar with distributed search or you've had to build services where you have two different tiers where there's an aggregation tier. It might look pretty familiar to some of you, but basically the aggregators route queries to leaves, and the leaves are basically sharded data. What this is solving for us is the intense read and write through rate. As you can see up there, we actually do read from Storm. We'll rebuild sessions on the fly if they're not already in memory. So it's not just a write outside of Storm. So if you have something like Memcache that does sort of a query layer on there, that's only solving the reads. So we actually need to solve the intense write through rate there too. Something pretty key too, when you stuff everything in memory, you start to get your bottlenecks become things like query processing, or basically being able to dissect that query. Well, the compiled plans are living on both tiers there to give us a boost in performance. So what we do in production is we're able to basically isolate different groups of aggregators. So Storm versus analyst aggregators, very different use cases. Storm, the reads that are occurring in Storm aren't necessarily merging data like an analyst aggregator would. So for us, it just made sense to sort of separate these and keep them on completely different paths. But the beauty of this is the analyst aggregators in Storm are literally hitting the same shards of data. So this is really what we achieve, and it's pretty exciting. We can do complex, basically even session queries that we've been talking about here at the time where peak concurrency is occurring on all of our streams. It's also provided us fault tolerance and storm bolts. You'll hear a lot of that in the community. If it's not baked into the framework to do fault tolerance of data that's residing in memory. Well, every time a session comes in, we're writing, and we're getting such great performance. We don't even batch the writes. It's literally firing writes out anytime data changes. Something it's also pretty interesting. Because the other streams that we're not presenting here, we do have use cases to basically do joins in real time. So whether we extend a Storm topology or we sort of glue different topologies together, we can now go do joins outside of Storm bolts, basically outside of the topology by the foreign key shards that MemSQL provides. It's also opened up the door, pretty easy argument, the complex data streams where we don't have necessarily static schemas. Well, we can alter the schemas on the fly without downtime or locking. It's pretty key in NoSQL stores. And now that there's a JSON type object, it sort of goes hand in hand with that, where we can really start to grow some of the complexities of persisting our streams. So wrapping all this up, we really wanted to leave you guys with some exciting thoughts. We basically built an architecture that scales to millions of players. It's probably beyond that, right? Because every tier is horizontally scalable. But what you see on the previous diagrams, we support millions of concurrent players. Horizontal scale everywhere, as I mentioned. But we're basically able to aggregate statistics across the entire U.S. as well as glue on to individual streams for complex analysis. And we like to say we gave a gift to a number of groups in Comcast because we're able to package up a real-time API into something that's familiar with them. So we're getting a little bit of praise for that right now. But more so, it's built a foundation for us. I think we're a good example of you can innovate off moving things in real time. And whether that's product innovation or tool innovation, having knowledge instantaneously or relatively instantaneously is pretty key for us. So now we know how to build alerts on complex objects, right? So, I mean, an example of that would be we can take video player data, merge it to CDN data in real time to form like a holistic view of the delivery life cycle. And there's also some innovation on, now that we know how to do real time, we can feed that data back to guides. So there's a little bit of work and whiteboarding going on with that. And by the way, a lot of these bullet points in the end really deserve a whole nother presentation. But there's a popularity-based CDN that was filed where, again, when we know things in real time, we can start making clever decisions on how to move content around a CDN to increase efficiency of our network. So that's pretty much what we have here, and I think we have time for questions. Yes?
Could you talk a little bit about challenges around the scale of operating an organization as large as Comcast and what we do around production and monitoring and things like that?
Yeah. Yeah, he's asking the challenges around productionizing and dealing with scale at Comcast. So quite honestly, that's why we've chosen like Cloudera as a stack in the Viper group, right? We don't use pure open source and try to glue things together ourselves. So we do sort of rely on Cloudera support for that. The MemSQL, we have support on that. I mean, Storm surely is the biggest challenge, right? It's not necessarily out of the box ready to be monitored by an operations staff. So we're doing sort of clever things on how do you monitor something like the bolts sort of dynamically appear in a cluster when you start a topology. So to go back to what Gabe was saying on discovery, we have to do things where we discover those bolts in order to monitor them with JMX, for instance. So Storm's definitely the harder part. Everything else is pretty manageable. You want to answer?
Sure. So it can actually have. Oh yeah, sorry. The question was basically that Storm does guarantees exactly one semantic by default, and so how do we get around that? So you can actually have an exactly one semantic using the Trident topologies. However, in our case, all the analytics message are tagged, have a timestamp, and so we actually don't process the events that are in the past. So if there is a repeat, we know that the events have been basically should be discarded because it's old anyway. We're always interested in the latest. Yes. Answer this one.
Yeah, he's asking the size of IT and engineering to build this. Yeah, the operations is much larger than the team that built this. I'll tell you that, but it's less than 5 fingers that built all of the real time, and you don't need all the fingers really. But yeah. We hire really smart people. I mean, we're the first to admit this is complicated stuff, right? It's not junior level engineering, but we're a pretty tight little group. But just connecting that with the complications of managing Storm, because of the complexities that come with real time, real time is sort of look like a experimental environment still for us. So it's production data, right? We can always go to Hadoop and get the raw data, but until we're able to really get a grip on managing it and able to hand it over to an operations staff, we're sort of managing the real time architecture. To build everything? Yeah. We've gone through iterations, so more recently we've integrated MemSQL. Before that we were running some things I probably don't want to talk about, but not too proud of what we were writing to before. But it probably 10 months, 9 months. A lot of iterations though, right? You learn a lot because there's no blueprint to do this. Top 3 use cases. Yeah, I mean, the first obvious one is just general analytics, right? I mean, that's knowing what's going on in IP video, right? What's hot, what's trending. Are there anomalies in bit rates dying, fragments dropping? So that's the interesting thing about our protocol is it's client side, but we're able to tell what's going on the server a lot too, right? So if you just look at CDN logs, you'll get time to serve fragments, but it doesn't tell you anything about the heuristics of how that player interpreted that fragment and whether. But yeah, it's Does that answer your question? Yes.
You mentioned server nodes with a variable bit rate, and I'm assuming that you're watching this, you're observing this, and then you have some automated, almost kinetic activity on the network.
Yeah.
Run into issues where maybe you got the algorithm a little wrong and you're starting things.
No, yeah, that's a great question because he's basically asking if we ran into any issues with being able to basically monitor bit rates, adjusting, and other metrics. What would have been cool to put on this slide is we actually send a bunch of threads into our own system, right? That we know what the data is, right? We know what the averages are going to be. It's basically like swallowing a pill with your camera on the pill. We can see what's going on through the entire data flow. So yeah, that was sort of a lesson learned. How do you know that you've got everything right? And that's part of it. You got to basically shove things into your own system and know the outcome.
What is the latency from time device issue events and goes through your pipeline, Flume, Storm, and out in your database?
Yeah, the question is the latency from the time events leave a player. Each player does do their own little incremental batch interval. Because one of the big requirements is when you put analytics on these players, you can't affect the video experience. So opening a socket and pushing out every single event that occurs is probably not the most efficient. So they do batch for small intervals. I don't even remember the range, maybe less than 5 seconds, 2 seconds for some. So that's why we're pointing out in the diagram there. The moment it hits Flume, we're less than 1 second. So the latency from a player to Flume, sometimes we can't control that.
So you talk about your analytic side, and the other side. So what are the things essentially using a tool or is you have open built system with what other things?
Oh, for the analytics part? Yeah, we built our homegrown. The question is, what do we have for looking at analytics visually, right? We've built our own sort of analytic portal, but what we're really interested in it's the real-time API because we can give that to other teams to build off of that. So when we were first building this, we had to give that visual insight, and we basically built our own. Whether you're using comment pushes to a browser or doing polls from an API, but yeah, we built our own portal. Yeah. Oh, sorry. Yeah. Yeah. Or he's basically saying clarify the persistence in real time, and it's in memory. Yeah. Yeah. Basically, it's persistent because it is storing to disk asynchronously. We can tune transaction buffers, right? So one thing I didn't put on there was we do two-way replication. So as soon as those events are coming in, they're basically pushed to two different servers simultaneously. And then a small transaction buffer, you're asynchronously writing out replicated data. So the chances of losing two servers are slim. So that's durability enough for us. Yeah. You're asking how many concurrent requests are being written at any time? Yeah, it's funny. We couldn't exactly talk about some of the numbers in Comcast due to our disclosure guidelines, but I can say putting it in the lab on bare metal, which, by the way, we're virtualizing now. That's the wonderful thing, too. We can virtualize everything from Flume all the way down to MemSQL, and we can use shared storage, which is what we're doing. But the configuration we have in the lab, we're getting anywhere from 50 to 75,000 writes a second into a leaf. So pretty amazing number for us. Volume? Sorry, what's it?
The number of events
Oh, yeah. Some of that we can't talk about. I mean, we did put on our abstract. It's we talked about Twitter ingest, and we're doing. Sorry to make you look that up, but we're doing more events than Twitter probably now. Yeah. Yeah. Is that it? There's one more. Oh yeah, the question is, we're open sourcing. Yeah, we're open sourcing the sink and the spout. Cool. Yeah, thank you.